So we're going to start with our second part of the multiplication rules with probability right now. And if you recall from last time, we started with the distinction between independent events and dependent events. And we saw last video that the independent events had a really nice probability um, rule. And that was that if the probability that A and B both happen, we just take and multiply the probability of A times the probability of B. Now, if we have dependent events, that can't happen. Or I shouldn't say that can't happen. That if we have dependent events, we can't use that rule anymore because getting A is going to affect the chance of getting B. So once I know A, that probability of B would have changed once I got A. In other words, in case the roulette wheel, if we thought about roll 1 and roll 2, well, if roll 1 actually affected roll 2, then the probability of roll 2 would have been influenced by this previous roll. All right. Now that's not the case in roulette wheel. In the roulette wheel example, we did have independence, and in the picking 5 Palestinians, we also had independence. All right. So again, we're going to figure out a rule for dependent multiplication. And really, it's a dependent division, all right? But if you remember from back in your algebra classes, multiplication and division are really the same thing. Multiply by a half, divide by 2, you get the same result. Now, we want to start with something fairly straightforward, and that is the notation. The probability of A happening, given that B has already happened, will be denoted by probability and then in parentheses A single slash B. All right, that's a single vertical slash B. So we'll often shorthand this language to say the probability of A given B. So the probability that A happens given that B already happened. Now, dependent events, when we calculate the probability, we often use the term conditional probability. So dependent events give rise to the term conditional probability. In other words, probability based on a certain condition or a certain something happening. So without further belaboring the point, when we have dependent events, the probability of A happening, given that B has already happened, is going to be equal the intersection of A and B on top divided by B. Now, what I mean by that is the probability of the intersection or just how many things are in the intersection if we're talking about sort of a classical probability example. And then given B. So this is how conditional probability is generally thought of. Probability of A given B, take all the things that are common to both A and B, and then divide by all the things that are in B. And what by that I mean all of the total number of things in A and B divided by the total number of things in B. So notice that the given part goes on bottom. We're given B, that's in the denominator. So conditional probability is often best seen using contingency tables. Now, a contingency table is just a table of data, and we've collected in this contingency table, we've collected about 15,000 adults from South Africa. Now, we test them on 2 different characteristics. First characteristic is whether they are male or female, and the second characteristic is whether they are HIV positive or HIV negative. All right. So we have 2 different traits. One is gender, The other is if they test positive or negative for HIV. And we can see the data displayed there. So reading this table, we see that the total is 15,054 people. The number of males, well, the total number of males is 7,647. The number that had HIV positive or that tested HIV positive was 1,482. And those males who tested HIV negative were 6,165 of those. And the females, 1,286, which tested positive for HIV, 6,121 that tested negative for HIV. You can see the total number of females there. And then here we can see the total number of people who tested positive for HIV, total number of people who tested negative. Now, if we just asked to read this table, we could ask some basic questions like, what is the probability that if we select a single person, so we're going to select one person at random, what's the probability that that person is male? So what we would do here is we'd say, well, we're looking for the chance that they're male. And that's out of everybody because it says I want to select one person out of the entire population, right? That's how it's interpreted. So what is the chance that out of the entire population, your pick is male? Again, this is conditional probability. We just take the total number of males, 7,647, and we put that over the 15,054. So let me write that out on this. We'd say, what's the probability that a person is male? Well, there are 7,647 males out of the total, which is 15,054. All right, so we'd end up with that probability. Okay. Now, the next question says, what's the probability that a randomly selected person has both characteristics? Again, we're going to select this person out of the entire group. So out of the entire 15,000 people, what's the probability that the person you select has both the characteristic of being male and the characteristic of being HIV positive? Well, we see here that 1,482 people are both male and HIV positive. If we're picking out of the total group, that 1,482 is going to be divided by the total group size. Again, that's just classical probability. So we take, 1,482 are the number of males who test positive for HIV divided by 15,054. Okay, so those are the normal probabilities that we've already done. Okay, the normal type classical probability that we've already done. Now what we're going to do is we're going to look at and ask for some conditional probabilities. All right, so we're going to look at this contingency table and now ask for some conditional probabilities. So the first one we ask for is, what is the probability that a randomly selected person has HIV given that they're male? So in this case, we are already given that they're male. We're given that they come from this group. Now, if they come from this group, I don't have to make my denominator the 15,000 number again. Since I'm given that they're male, it's going to be out of 7,647. And those males that test positive for HIV, so since I'm given that I'm working in this very top row, those who test positive for HIV are only these 1,482 males. So hopefully you saw that. Let me write that down. 1,482 out of, again, since we're given that they're males, we're just looking in the group of males and I'm ignoring everyone else. 1,482 out of 7,647. Okay. And so what we saw here is that we can just focus on this very top row if we're given males. And similarly, if we're given females, we can basically ignore everything except for that middle row. Let's look at the next question. Next question says, well, what's the probability that a randomly selected person has HIV given they're female? I'd like you to, again, push pause, figure it out. In about 5 seconds, I'll come back and state the answer. All right, so since we're given that they're female, I ignore everything but the females. Excuse me. So I ignore everything but the females in this middle row. And so what's the probability that you pick one female at random? Well, that has HIV, it'd be 1286 divided by 7407. So to write down my answer, we go 1286 because that was the number of females who had HIV out of 7407 because that's the total number of females. Now I want you to just take a moment to think about what that meant for our general rule. Remember, our general rule said probability of A given B was both traits, those with both traits on top, divided by those with a given trait. And so we see that the probability of having HIV given that you picked one of the females is equal to, we'll take the number of females with HIV, put that in the numerator of the fraction. So this would be females with HIV. And since we're given that, I should say females with HIV, since we're given that they are female, that's what's going in the denominator. So that contingency table kind of tells you where that conditional probability rule is. And notice again, the conditional probability rule is more of a division rule than it is a multiplication rule. But you can write it as multiplication just using some simple algebra. Okay, I like to see it as division. I think that makes more sense. But you can use some simple algebra to make it into a multiplication rule. So I'd like you to try this one. And this one is going to highlight a couple of things about conditional probability. So push pause, read the question, and try to do it. All right, so we see now that the question asks for the probability that a randomly selected person is female, given that they test positive for HIV. Now, in this case, we're given the HIV positive part, and we're looking for the female part. And basically, it's a change in denominators. Instead of just given females, so ignore everything except for the second row, I'm given HIV positive. So I'm going to ignore everything except for this first column here. And so I see that since I'm given HIV positive, I'm in this group of 2,768 people. And the females in that group comprise 1,286 members. So the probability that a randomly selected person is female, given that they have HIV positive, is going to be 1,286 divided by 2,768. Let me write that down. Oh. So 1,286 divided by 2,768. Now, I do want to mention right now, this is a good time to mention that there's 1,286 out of 2,768 females. Obviously, I've just left these as big fractions in all of my answers, all right? But when you're doing this in Moodle, it's going to ask you to reduce that, excuse me. In Moodle, it's going to ask you to give a decimal, 0.4646. All right, in this case, in this final case. So 1,286 out of 2,768 gives me that decimal. You could have also reduced a fraction. I'm not going to, but it turns out you can reduce it in this case. So Moodle's going to ask for the decimal. On the test, I'd be more than happy if you just gave me the fraction. All right. So Moodle's going to ask you for this decimal. On the test, just leave it as a fraction. If you want to give me a decimal, that's fine, but the fraction's probably going to be easier to see. So that is conditional probability, how to get that from contingency tables. Now you might ask, well, what if we don't have a contingency table? What if we just have some data, but it's asking me for conditional probability? So let's do this example to illustrate that. So let's assume that there's this brand new test for malaria. And this test that comes out is correct 98% of the time. So that means 98% of the time, someone with malaria will test positive for malaria. And 98% of the time, someone without malaria will test negative for malaria. Now, we know malaria is not a very prevalent disease in the United States. We get some cases. Usually, it's about 1 in every 150,000 people will contract malaria inside the United States. So it's, again, not very common in the US, but it is common in other parts of the world. So let's pretend that in the United States, some politician gets the idea that they want to eliminate malaria from the United States. Okay, so their goal is to get rid of malaria. And so what they propose is that they propose testing everybody in the entire United States and seeing if these people have malaria or not. All right. And then when they test positive, we're going to quarantine those. When they test negative, we're going to let those people out. So they give it to everybody in the US. Now, assume that this actually would happen. Obviously, it's a made-up example, but assume that the politician gets to test everybody. And then I ask, so the politician tests everybody, almost 300 million people in the United States. So they test almost all 300 million people. And then I get groups of people who test positive, groups of people who test negative. I have a group of people with the disease. I have a group of people without the disease. So we can ask, if we test everybody in the United States, what's the probability that a person has malaria, given that they tested positive for it? Now I know what the gut feeling is that we just saw that the test is 98% accurate. But that 98% is not answering this question. That 98% is saying, well, what proportion of the total population does the test get it right for? 98% of the time, the test gets it right. Okay? But what that doesn't say is that after they test positive, well, we have this big group who tests positive. Which ones of those actually have the disease and which ones of those don't? So what we're going to do on this example is we're going to create our own contingency table. Now, this is not the only way to do this problem, but it's a fairly effective way to do this problem. So we can break up the two characteristics as either having or don't having malaria. That's the first characteristic. The second characteristic is whether we test positive or negative for the disease. So whether the test says we have malaria or whether the test says we don't have malaria. So let's engineer this table and figure out how we could fill this in. All right, this contingency table. Now, I'm going to insert a table, or draw a table, sorry, in my Word document. So what did we say? We wanted to test positive. No, I'm sorry. I want to make sure that, so we're going to have malaria or not have malaria. And then we'll do the total people who have it. This is the group who test positive for the disease versus they test negative. And then again, we'll look at the total. Now, how can I write a table? Again, let's assume, I'm going to use a nice round number. Let's assume that there are 300 million people in the United States and we get to test them all. There's actually a little bit more than that. There's a few more than 300 million, but we'll round it to 300 million. Okay? Now, first step is determining how many people actually have malaria. And this is going to come from the fact that about 1 in every 150,000 people will have malaria. So if we multiply that times my 300 million, we see that we get about 2,000 people in the United States are likely to have malaria. Now that is not a big number out of 300 million. You take 2,000 out of 300 million, and that means 299,998,000 people will not have malaria. So that's a good sign, good thinking, because you probably don't have malaria. Right? Good way to say that we don't have malaria. And again, I'm getting that 1 in 150,000 because it says we also know that malaria affects every 1 in 150,000 people. Okay. Now, when we go up vertically, this is where that 98% of the time comes in. 98% of the time I get it right. So if you think about it, 98% of these 2,000 people should test positive because if they have malaria, the test getting it right would say that, yeah, the person has malaria. And what's that mean? That means that 1,960 people will actually have malaria. Now, 2% of the time out of that group, the test is going to get it wrong. And for this group, if you have malaria, the test getting it wrong would mean that it tests you as negative for malaria. So we can multiply that and get out of 40. So 40 people out of the group who have malaria will test negative, but the vast majority, 98% or 1,960, will test positive for malaria. Now let's go to this next but bigger group. Okay. Now this next bigger group does not have malaria. So 98% of the time, this group should test as negative because they don't have the malaria. The test getting it correct would say they don't have it. So take 98% of 299,998,000, and we see that the group who tests negative who didn't have malaria comprises of about 293,998,040 people. Okay? And in a similar way, 2% of this large group, so 2% multiplied by 0.02, hopefully we all know how to say take 2%. We move the decimal place over 2 spots, and 2% of a big group is just 0.02 times that big group. And what you get in this case is that 2% of almost 300 million people turns out to be a lot of people. It turns out to be about 5,999,960. Now, that is a big, big group who test positive but don't actually have the disease, right? So let's, for completeness, fill this out. Those who test positive, 1960 plus that group. So we take 1960 plus the almost 6 million, and you get just over 6 million. And similarly, you get just about 294 million when you add all of those up who tested negative. You get 293, 998, 080. All right. So notice how we created our contingency tables just based off of the percentages given. All right. So we created this contingency table. Now, what is the probability that they have malaria given that they test positive? That was our original question. What is the probability that they have malaria given they test positive? If I'm given they test positive, then we're just looking at the group who test positive. And those that have malaria, well, that's that 1960 group. Those who test positive is the 6,001,920 group. So we get, I don't like these little lines. Let me try to fix that. 1,960 divided by that 6 million number. Okay. Now, if we take 1,960 and divide it by that 6 million number, we again get scientific notation. We get 3.27. Oops, let me write that in scientific notation. We get 3.27 times 10 to the negative fourth, which again, just writing this down would be 0.000327. Okay. So notice how low that probability is. Okay. That probability is extremely low. So the probability that the person actually has the disease, given that they come from the group of 6 million who test positive, is very low. It's well under percentage point, right? 1% would have been right at the second zero there. So we're like 0.03% there. So this is how we could create a contingency table and have that contingency table determine my probability. Now, by the way, the reason this is so low, I hope we all see, is because of all of these people who actually tested positive for the disease but didn't have it. In health, that's called a false positive. All right, that's also called a false positive in statistics too, when the results look like a positive but it's not actually so. And false positives are a big problem, okay? If you think about Even when the chance of getting a false positive is low, like 2%, if I have a big enough group, I might create a lot of false positives. This is also an issue in statistics. There's a lot of times people will be looking for some sort of a statistical correlation between two um, two things. So they'll do a scientific study, and if you have a 5% chance of getting a false positive, and we have 50 studies out there, it's fairly likely that one of those studies is going to end up with some sort of a false positive. All right, we saw that in the Palestinian example, right? We had a 6% chance of finding somebody who liked ISIS. So we had this really low initial probability, but um, but when we group together 50 people, we're bound to get a bad result. And this is why replication is so important, okay? We don't want to base our judgment just on maybe one study. We want to do lots of studies. That sort of minimizes the false positive effect, okay? Not necessarily in healthcare, but when we do lots and lots of statistical studies, okay? In healthcare, false positives are a big deal. And you might say, well, why is a false positive a big deal? Why are these 6,000 people in healthcare, eh, they don't have malaria, so it's no big deal if they tested positive. Well, it is a big deal because all of those 6 million people, if we test positive for malaria, are going to end up having to go to the doctor and get a second test. And those 6 million people will clog up the system. And a lot of the people who actually have malaria will probably get stuck in the back of the line and end up, dying or very ill because they ended up in the back of the line and it took them too long to see a doctor. All right. Hopefully, we all know that speed, the timing at which you see a doctor is important. The earlier they can detect disease, the earlier they can detect cancers, the earlier they can detect anything, the better chance you have of living through whatever the disease is. All right, so false positives are both a big deal in healthcare and are a big deal in statistics overall. And so this example was not only that you see how to produce your own conditional probability through a contingency table, but also shows you the dangers of false positives. Now, what if I don't want to do a contingency table? If I don't want to do a contingency table, I don't necessarily have to. As long as I know probabilities, I don't necessarily need to find the actual numbers of people. All right. So last example, I'm sorry, the malaria example, we assumed that there were 300 million people in the United States. And that created our contingency tables, which gave us our conditional probability that we were looking for. But what if I don't know raw numbers? What if I only know probabilities? Well, the general rule can be translated into probabilities as well. And so all it is probability of both traits divided by the probability of the given trait. So instead of the number of individuals that have both traits divided by the given trait, we can just replace number of individuals with probability. And we still get this exact general rule. Again, some people will write this as a multiplication rule. They'll just take probability of B and they'll multiply it on this side, on the left-hand side, and then they'll get rid of dividing it on the right-hand side. So, basic algebra, that probability rule, that division rule is also a multiplication rule. So let's see how we do this. Let's take an example done with lab rats. Now, this was a real study, and what happened was a group of researchers, I believe they were from Sweden, filled up a water tank. And essentially what happened is they put these rats in one by one, and they figured they were timing how long it would take them to drown. All right. So they separated these out into a control and experimental group. All right. Now the experimental group was given a platform. All right. They were placed in the water tank, and there was this clear translucent platform that would come up. Again, it was a mechanical device. It would come up, and for a few seconds, the rats could stand on the platform without swimming. And then the platform was taken away. And then the rats swam until they drowned. Now the control group was just placed in the water, and those rats swam until they drowned. I know what you're thinking. This is a weird example, right? But it is something that actually happened, and you can look that up if you want to. Now, I have made up numbers on my example, but this was an experiment that actually happened, and I'll tell you sort of why that happens at the end here. So basically, there were platform rats who were given the platform, and then there were rats who were not given anything. And it's recorded whether the rats swam less than 10 minutes or over 10 minutes. So here were the results of the study. It says that the probability of picking a platform rat, one that was given the platform, in the experiment is 0.6. So about 60% of the rats chosen were given the platform. The probability of picking a rat which had drowned in under 10 minutes was 0.7. And the probability of picking a platform rat which had drowned in under 10 minutes is 0.3. So in other words, the probability of having both the platform trait and the drown in less than 10-minute trait is 0.3. So I want you to try to use the general rule on your own to answer these two questions. Push pause on the video. Well, first off, read the questions, push pause on the video, and then try the questions, and then in 5 seconds I'll come back and show you how this was done. All right, so hopefully you've done that. First question says, what is the probability that a platform rat is chosen given that the rat has drowned in under 10 minutes? So let me figure out this probability. What is the probability that platform rat was chosen given that we drown in under 10 minutes? Okay. Now, what does the general rule say? The general rule says that what goes on top, the top part of the fraction, is those rats with both traits. So platform and drown in under 10 minutes. I'm just going to simplify that in that way. What goes on the bottom of the fraction? Well, those who have drowned in under 10 minutes. In other words, the given part. Since we're given that the rats that drown in under 10 minutes, we don't have to look at any other rats other than those who have drowned in under 10 minutes. So, in short, what kind of answer are we going to get? Well, which rats had both traits? We don't know the number of rats who had both traits, but we do know the probability of the rats who had both traits. Probability of picking a platform rat which had also drowned in under 10 minutes was 0.3. So on the top, I just have to put 0.3. And on the bottom, I just have to find the probability of picking a rat which has drowned in under 10 minutes. Again, that's 0.7. Now, just like always, right now, that would have been a perfectly fine answer for the test. You could put 0.3 divided by 0.7, and that's a fine answer on the test. On Moodle, you'd have to divide that. 0.3 divided by 0.7 is 0.4286, rounding it to 4 decimal places. Again, this is a probability, so we're rounding it to 4 decimal places. And that would have been the answer to that first question. Now, the second question says, what's the probability that a rat has drowned in under 10 minutes, given that the rat was one of the ones given the platform? So what we've done is we've flipped which one we were given and which one we were looking for. So now we're saying, what's the probability that they drowned in under 10 minutes, given that they were a platform rat? Okay. Now notice what's going to happen on top. Drowned, we're going to have both traits. Those rats with both traits are going to go on top. And on bottom, those rats who are the platform rats, well, those are the ones who go on bottom. Notice that being a platform rat and drowning in 10 minutes is the same as drowning in under 10 minutes and being a platform rat. So we still get 0.3 on the top of our fraction. But on the bottom of our fraction, since we're given the platform rats this time, 0.6 is the probability of being a platform rat. So the bottom of our fraction is going to be 0.6. Again, at this stage, you're good to go in terms of the test. On Moodle, they'd ask you to do divide. 0.3 divided by 0.6 becomes 0.5 overall, or 50%. Now, you could have done this also using complements. Obviously, we know that if 7.7 was the probability who had drowned under 10 minutes, we would also know that the complement of that is those who lasted more than 10 minutes. And platform rat being 0.6, well, we can know the complement of platform is not a platform rat, so the other group. So we could figure out 0.4 is not a platform. The probability of picking a rat which is not a platform rat is 0.4. So we could have done all of this, and we could have given some more probability questions, but I think that suffices to show you how that dependent probabilities go. All right. Now, one thing this does show us is it shows us, well, in all of our dependent probabilities, hopefully you've noticed order matters. The one you're given is very different. The probability is very different based on the trait that you were given. All right, so if we're given drown in under 10 minutes and looking for platform rats, that is very different than given platform rats and looking for those who drown in under 10 minutes. Okay, so order of dependent probability, order of that general rule is very, very important. Okay, now I said I'd talk to you about the rat example. Why would anybody do this? Why would anybody, are they psychopaths that wanted to, punish rats or something? No, this was a psychological experiment. And basically what these rats were doing, they were testing a hypothesis that having the hope of finding that platform would make these rats want to swim longer and try harder. Okay, so they were testing the hypothesis that hope actually makes individuals try harder, swim longer, those types of things. Okay, and it turns out if you would have, these are sort of made up probabilities, but if you were to look at the actual experiment, I'm sorry I didn't cite it, but if you look at the actual experiment, what happens is that those who were given the platform rat those who were given the platforms did in fact swim longer than those who were not given the platforms. And so we can conclude that having the hope of finding the platform did make these rats swim longer. And so I don't know if that's any good news for us or not. I guess if there's any takeaway, you should always have hope, right? All of us, just like the rats, die in the end, but hopefully that hope will make us try harder, live longer, do better things in our lives. All right? I don't know if that's a good note to end on or not, but that is the end of chapter 3.